So we're going to go ahead and get started now. Again, thank you for joining us on today's webinar, where we're going to introduce one of 3D Systems' customers, Bylink, and talk about how they've been able to break speed barriers and open up a lot of new opportunities with 3D printed injection mold. Our speakers today on the webinar are myself, Tom Sharon. I'm the VP of Product Marketing at 3D Systems, and I'm very pleased to have with me today Ray Zaganto, who is the president of Bylink, and Frank Zaberna, who is the R&D director at Bylink. And the three of us are going to go through a brief presentation, and then we're going to open it up to live Q&A with everyone who's in the webinar today. And the way that we do this Q&A is you can type your questions into the questions box in the GoToWebinar window, and we'll be reading those questions out verbally at the end of the webinar and answering as many as we can. Now, typically with our larger webinars like this, they're very popular. We're not able to get through everyone's questions, but we'll try to get through as many as we can within the hour. And if we don't get to your question, we will answer it offline. So feel free to type your questions at any time during the presentation or after during the Q&A session. With that, let me do a brief introduction to 3D Systems. So 3D Systems is the company that makes the 3D printers that Bylink is using. And we're known for providing the most advanced and comprehensive 3D digital design and fabrication solutions on the market today. We're really proud of our history of innovation and technology. The company invented 3D printing originally with our SLA, or stereolithography, print technology, and we commercialized that in 1989. We also invented selective laser sintering, or SLS printing, and we were the first to commercialize that in 1992. The company invented color jet printing, which is CJP, and brought that to market in 94. And we invented multi-jet printing, and we're the first to commercialize that in 1996. And the technology that we're going to be talking about today is the last one on that list, MJP, or multi-jet printing technology. So as a company, 3D Systems is well known for having by far the broadest line of 3D printing offerings available. We go all the way from home use 3D printers that are available for less than $1,000 all the way up to production level systems that can print in a variety of different materials, including metals, up to and over $1 million. And there's a whole slew of options in between. And we offer all of these different printers because there are so many different applications and needs for 3D printing, different needs for speed, accuracy, material properties, and so on. So there are a variety of different options. Now, when we talk about the applications of 3D printing, we can broadly categorize them into 5 categories. The first and sort of the earliest in the product development process is the idea of printing a 3D model for communication. And this is all about making aesthetically pleasing models that have all of the details and may or may not have color involved in them so that you can communicate ideas. This is great for selling new design ideas. Architects use it to sell clients on design ideas before they've spent the time to actually go through and make the very detailed models and so on. So it's really about the beauty of a 3D printed part when we're talking about communication models. The next step in the development process is really prototyping or validation, and this is all about printing functional parts that approximate or exactly match the properties that you're going to be getting from a production part later on. And of course, the value that 3D printing offers is that you can have your parts essentially instantly. You don't have to go through a tooling process to get to those early prototype parts. And so you can iterate and come up with many different ideas, and every piece that you print can be different, and you can have them in your hands usually in a matter of hours from when you've designed them in CAD. The next step along the way is to make tooling. And this is really around the pre-production process. And that's what we're going to be talking about today largely, is rapid tooling, where you're actually printing tools or patterns for tools, and then you're using injection molding or other manufacturing processes to actually make parts like you would any other part. It's just that the tool that you're using to make those parts has been printed, as opposed to CNC machined or the other methods of making tooling. Of course, you can go into actual series production with printed parts. We have a lot of customers doing this with our metals machines now, and some of our plastics machines as well, that will make end-use production parts directly off of the printer. And then we have mass customization as a very important area for 3D printing, and this is where a lot of the healthcare applications of 3D printing are used. And when we say mass customization, we're talking about millions of unique parts that fit individuals. And so, of course, if we're looking at things like a bridge for your teeth, as you can see in the image there, of course, that's going to be custom to you and only you. And there's no additional cost in a 3D printer to make every single piece custom, which is one of the great benefits of printing. With that, I'm going to hand it over to Ray so that he can introduce you to BuyLink and continue on talking about how they're using printed injection molds. Ray?
Thank you, Tom. Good morning, everyone, or good afternoon. Thank you for this opportunity. I want to give you a brief introduction to BuyLink and who we are. We're a high-volume manufacturer of complex metal and plastic components and assemblies. Just to give you a sense of what we do precision metal stamping through 600 tons. We do injection molding through 500 tons horizontal, 350-ton vertical. So what are we doing on a webinar talking about prototypes? In a nutshell, we've been doing this for 53 years across multiple demanding industries for the very best and biggest OEMs around the world. The lesson we learned very early is that projects that launch the best, run the best, and have the best economics are the ones that we're able to get involved in early to help influence the design, ultimately improve the manufacturability. You know, along the way with high-volume metal and plastics is you've got to have some tooling expertise. We're a very tooling-intensive business. We build all of our own tooling for the progressive dies that we run and the injection mold tooling. So to give you a sense of scale, last year we built over 600 tools for our own use across all of our facilities. So we know tooling, and we know what's involved in making parts manufacturable. Our biggest impact happens when we engage with engineers. We call it E to E. This year we rolled out the hardware store by BuyLink, and what that is, it's a place for engineers, by engineers, to collaborate with our technical staff and get access to our technology and resources. The idea is to let our clients, let them test, talk, tinker. We want it to be an extension of our customer's model shop with access to a ton of global manufacturing horsepower. Part of what we do in the hardware store locations, and we have one in Raleigh, North Carolina. We're in San Diego, we'll be opening up there soon. We host events for our customers, and the idea is bring technical people together to talk about the challenges that they face, blend in our tooling expertise, and see how we can help solve problems. We talk about the Midnight Lunch Lab, which is housed within each of our hardware store locations. And what that is a nod to Thomas Edison. In our perspective, he was a master at bringing together teams of people with diverse backgrounds to define and solve really big, worthwhile problems. And we like that as kind of a basis and a philosophy for us in our hardware store locations. What we saw is the opportunity with 3D printed injection molds. You know, a few years ago it became clear to us that our customers across all industries required us to do more faster. Improvement needed to happen by an order of magnitude, not incrementally. The process needed to happen in days, not weeks. Design for manufacturability needed to happen real time and at every step of the development process. And we had to have speed and flexibility to accommodate changes. So our ultimate goal was, how do we get to the point where we can come up with a few parts per print in the specified material that confirms form, fit, and function, and we need that now, not later. So how did we get here? As Tom mentioned earlier, you know, complexity with additive manufacturing is free. Tooling is complex. By extension, additive manufacturing should at least be part of the solution. We learned that it's really more than that. We did some preliminary research and saw that printed molds had been attempted. I mean, anybody that checks on online and looks for what's going on YouTube, the problem we saw was that it was the same spoon and impeller have been showed on YouTube for years. There was really no evolution in it. So we started experimenting. We placed a small initial bet. We bought a cube printer for $1,000 and started goofing around with it. Had some reels of PLA, and you know, you do what manufacturers do, you tinker with it. And we saw what it was good at, we saw its limitations, and most importantly, it got us asking more questions. And what we found with the team from 3D Systems is they were a really big help and provided a lot of resources for us. Ultimately, when we looked across the industry, we settled on the ProJet 3500 HD Max as our technology base and platform that we wanted to build off of to get to the next step, which was to 3D print injection mold tooling for prototype samples. What we learned that kind of defied our original expectations: printed molds can take a lot of heat. As Frank will discuss in some of our case studies, we're running everything from polypropylene through liquid crystal polymer through printed tooling, and heat is not the enemy of the tool, which surprised us. We thought that was going to be a limiting factor, and it wasn't. Compression is your friend. The nature of the materials and how it's printed, they can take and respond very well to compression, which works well in the injection molding process. The longest mold print we've had so far has taken us 12 hours, and that's really a function of Z height for the print. And at that time, because of the table size we have with the 3500 HD Max, we actually printed 2 sets of tools at the same time. Production quantities that we see from the printed tooling, it's been anywhere from 5 to 200 pieces, depending on the molding material that's required and the nature of the part geometry. And it really does allow our engineers and designers to iterate in hours versus days in actual production intent materials. So it has checked all of the boxes that we needed. We've even been able to do multi-material. We've done insert molding, and we'll share examples of those case studies with you right now. So with that, I'll turn it over to Frank Zaberna, and he can walk you through the applications. Frank?
It's an example of one of the parts we did in LCP. The tube is about 7.5 inches long. Had a fairly thin wall section, so you could see where we injected from. The material, if you clamp it upright, will take enough pressure that you could fill that whole length in the little undercut that was at the end. So once you learn these molds, you could do a lot with it. You could see our temperature was 650. The hottest we've injected into these molds was a little over 675, a special material we were running a couple of weeks ago. So they will take the temperature. This particular mold, we made better than 24 parts out of it with the LCP material. So it will take the heat, and the tolerances are exactly what you would expect out of a production tool. The parts are exactly to print. The mold's making the right size. There's not a problem with warpage or twisting or anything else. The parts are extremely stable in these molds because of the way they cool.
And then the temperature, the thermally inert.
What we find with this material is it's pretty much, it's dead to temperature. It doesn't really absorb a lot of heat, which I think is why you could inject into it at such a high temperature. When you go to cool parts, you have to be careful. It'll take longer to cool than you're used to because it won't remove the heat from the material. But an upside of that is you get extremely flat parts because they cool so slow and evenly. So that's one of the reasons, once you learn how to use that to your advantage, that it doesn't absorb the heat, it lets you inject some pretty interesting parts. Cooling the material in the mold isn't an issue, so you could keep it flowing longer and really fill up into some thin sections. This was a part we did in an elastomer. This was a test part, so it was still in development. We did 4 spins on this part, with the 6 days that it shows, and that included shipping them. Basically, the customer would get the parts in the morning, check what they needed, do a modification. I would run a mold overnight, shoot new parts in the morning, ship that afternoon. So you could really turn parts quickly. We printed the mold last night. It's running this morning. I loaded the tables with 2 molds this morning that are going to run parts tomorrow morning. Those are ABS gears, so they're fairly involved parts. And again, the material's a little higher temperature. But given the right part, the right size, you could easily turn these in a day. If you get into steel cores and things like that for some real thin sections, it's going to take you longer to make the steel. But this particular mold that you're looking at in this picture, that was about 12 hours to make. And the part was exactly to print. The finish was nice. There's actually some lettering that was on the part that doesn't show up in this view. But it was exactly to print, and they ran in, did their testing, figured out where they needed to make their changes. We made them another part. So you could do spins in development in a time frame that is really unbelievable. It's definitely possible to have molded parts out of the proper material in a day. It depends on the configuration, but a part like this, it was a day.
And one thing to add, Frank, the parts, we don't do secondary trimming and deflashing and those types of things. And if you run elastomers, they can have a propensity to flash pretty easily. And these parts, the molds clamp up nice. The parts come out clean. We basically degate and pack.
Right. We don't have a problem with flash on these parts at all. At a given pressure, it's like anything else. If I go past the clamping pressure on my machines, which is 10 tons, they're going to start to gap. But if we clamp them up properly, flashing's not a problem with these molds. The parts come out clean, regardless of the material type.
Okay.
Yep. We do insert molding with it. This one here, the gold-colored parts, those are metal inserts that we put into the 3D printed mold and then shot the contact housing around them. So we do quite a bit. We've insert molded metal contacts. We've insert molded plastic tubing, fiber optic bundles, actually other plastic parts inside of another piece of plastic in these printed molds. So pretty much anything you could do in a metal mold, any type of tooling that you would do in metal, you could do in this up to a given size. Normally our molds are about, we go with a 4 inch by 4 inch mold. So if you could stay inside that size range, it'll handle most anything. But different types of, like I say, the insert molding, whether you're molding in tubing or fiber optic bundles or metal, you could do that process with this tooling and still be able to do it in a day.
So now what I'm going to do is talk to you about the Project 3500 series printers. As Ray mentioned, what BuyLink uses is the top end of the 3500 series, which is the Project 3500 HD Max. But there are several models available that offer different speeds, different build sizes, and different accuracy and resolution offerings, and of course come in at different price points. But the 3500 series is a a printer that prints functional plastic parts in high definition, and it can be used right in your office or out on a lab floor or a shop floor. It's quiet enough and clean enough that it can be used in an office, though, and a lot of customers do choose to use it that way. The Project 3500 series prints really beautiful functional plastic parts, and you can see just a few of the different parts here. We can run materials that are white, black, clear, and we have a variety of other materials I'm going to go through in just a moment. But you can see some of the different applications, and a lot of people are using Project 3500s to print prototypes or to print some end-use parts. And then, of course, we have the more novel use of the Project 3500 to actually print tooling, like what Bylink is doing. Another example of printed tooling is the image you see in the upper left-hand corner, which is hydroforming of sheet metal. So that that piece that you see underneath the formed metal part is a printed mold pattern that is then hydroformed at many tons of pressure. And as Frank and Ray were talking about earlier, the materials that come out of the Project 3500 and the parts that come out of this printer stand up very well to high pressures, so they can be used in applications like hydroforming as well. These printers are known for their really, really excellent detail resolution. You can see some of the images here show the level of detail that you can get. This little Buddha statue that you see over on the left-hand side, just to give you an idea, is only maybe 2 or 3 inches tall. That's a few centimeters tall, and that you can see all the fine details on it. So, you know, parts coming off of the Project 3500 are aesthetically pleasing. They can have all of the detail that you want, and we offer some really beautiful materials that you can print in. But more importantly for most people is that they're very, very accurate. They have great fidelity, and you can see every detail, and you can get every functional component that you need out of this printer. The Project 3500 uses, as I mentioned earlier, our MJP technology, which stands for multi-jet printing. This is a technology where we're jetting out a photopolymer and curing it with UV light. And one of the benefits that our MJP technology has over other printing technologies is you get really consistently sharp edges and corners and very, very smooth sidewalls. You can see some small parts here with really tiny holes and features in them, and they all come out beautifully, which again, there's some aesthetic value to that, but more importantly, there's real functional value when you've got parts that need to mate with other parts or have very small hole features and things like that. Get very crisp, sharp definition out of the Project 3500 that you don't necessarily get out of many other print technologies. These printers are known for their accuracy and precision. These parts that you print will snap together. They can be assembled very effectively together. And in the example that Bylink is using for printed molds, they will clamp together and you won't have flash and that sort of thing, which is another benefit of the accuracy and precision and edge definition that you get out of the Project 3500. And the parts that come out of these printers are strong. They're strong enough for real-world use in certain situations. A couple examples here are the one on the left, the upper and lower image. What you're seeing there is Nissan Motorsports in Australia runs their race cars, which are V8 supercars. This is sort of Australia's equivalent of NASCAR, where they run these cars with 3D printed components in them. And the particular component that you see there in the upper left is a blower motor housing that was printed because the stock blower motor housing that the team was sourcing was breaking under the stress of these vehicles running, in 100+ Fahrenheit temperatures for, a lot of time, very high vibration, high heat environment. And the stock parts weren't able to take it. So they redesigned the part. They made it stronger. They knew exactly what they needed to do, and they're able to print those on a Project 3500, put them in their cars, and race with them. And on the right is another BuyLink mold example. You can see the mold up top and the part that came out of the mold down below. And as we've been talking about, the materials that we're using in the Project 3500 are coming out plenty strong for this application. And speaking of materials, we offer a variety of different materials. There's different colors with ABS-like performance. We have materials that are biocompatible, that are USP Class 6 compatible for medical applications. We have translucent materials, and we even have castable materials so that you can print and then cast in a metal of your choice off of the Project 3500. And I should mention that we're talking about the Project 3500 plastic 3D printers. We also have a line of Project 3500 wax 3D printers. And we don't talk about that in this presentation, but the wax 3D printers are used to print sacrificial patterns for a variety of different casting applications. So some of the other benefits of the Project 3500, and one that it's really well known for, is its melt-away wax support. So like all 3D printers, the parts that are being printed on this machine need to be supported while they're being printed layer by layer. And the way that we do the supports in this printer is with wax. And so it's very simple and essentially hands-free to post-process these parts. You take them out of the printer. They've got wax holding them up as they're being printed. So you take the whole part out with the supports on it. You put it in an oven, and the wax simply melts away. So it's almost entirely a hands-free process. You do a little bit of hand work after you've put them in the oven, and they're ready to go. And one of the huge benefits of this is that because you're not manually cleaning these parts, there's little to no risk of breaking any delicate features on the parts as you're trying to remove the supports, because it's just melting away. There's no special waste disposal required because it's wax that's coming off of the parts. And it's a very efficient use of the support material because, in fact, it's not solid wax that's printed. It's about 40% air that is left inside of the wax support structure as well. So it's a very efficient use of support material. The Project 3500s have long-life print heads, very low maintenance on the print heads, and they come with a 5-year warranty, which gives you peace of mind and so that you know that you're going to get 5 years of good, strong use out of the print head in these printers. Again, as I mentioned earlier, they're known for their efficient material use, and we have Android and iPhone apps so that you can manage and monitor prints remotely with the printer. So again, it's an easy-to-use system. So why choose the Project 3500? Just to summarize, because you can quickly print superior quality functional plastic parts. They're very high resolution with sharp edges, crisp details, and smooth surfaces. It's an easy-to-use printer. It's intuitive. And ultimately, it's all about being able to test more ideas faster and very economically. So now I'm going to turn it back to Ray and Frank to talk about some of the results that they've seen from using printed molds.
Thanks, Tom. Just to run through the kind of the high-level benefits that we have seen across these 3 applications, and we come across new ones every day. The first part we looked at with the high-temperature material, the LCP, that was part of an 8-part package that we had received from a medical device client of ours that we work with, major player, major company. And what this process allowed us to do and allowed our customer to do, because of the ability to compress the design and development schedule, we actually helped them pursue a parallel project to one that was had already started a number of weeks earlier. And basically, in about a 4-week period, we had a working model in production materials that concluded at about the same time as the original project. So it allowed our customer to basically double down on their development effort based on the much shorter lead times to be able to bring the product to market. The elastomer that we worked on, as Frank mentioned, it really helped our customer with an internal project. Without the speed that we were able to come up with, they would have really missed the window of opportunity. And again, the speed with which we're able to do this and the flexibility that it brought was a huge advantage for the customer. And these are major players that we're working with. These are people that understand what best-in-class looks like across all segments of the supply chain, and speed and accuracy still wins. The insert molded project that we looked at, we not only made a lot of changes to the plastic, but to the metal as well, allowed our customer in this application to dramatically improve the overall performance. Again, we're tooling experts. We're able to bring DFM support all the way through the process, and for the customer to be able to come to a single source with these capabilities made it a whole lot easier for their engineers to be able to communicate. So we're seeing time and time again across multiple industries the ability to bring the speed, the flexibility, and the real-time DFM really matters. And having the 3D Systems machinery, the equipment works, the process works. We currently have 3 of the 3500 HD Max machines in our organization. We're planning to add several more over the course of this year. So it works, and we're very pleased with the support we've had from 3D Systems, and look forward to bringing some more innovations in the future.
Excellent. Thank you, Ray. All right, so that wraps up the presentation portion of the webinar. We're now going to move into our live Q&A session. And my colleague, John Paul Velasco, is going to come online, and he'll be reading off your questions, and then we'll do our best to answer these.
So the first question we've gotten is, how do you predict production mold cycle times using this approach?
We'll still use the traditional simulation tools. We run mold flow analysis, so the cycle times don't really correlate because, as Frank had mentioned about the thermal characteristics of the printed tooling material versus what you would see in a steel mold. So you kind of need to look at it a little differently. They're independent of each other. Printed mold cycle times will be just kind of by definition and just based on the thermal characteristics of the material, they're longer. But again, we're focused on using this process to come up with that first, 1, 5, 10, 20 pieces right now. In parallel, as we're using what we've learned in the development process, we'll go back to our the regular simulation tools plus our 50 years of experience to dial in a production cycle time.
Great. Thank you so much. So the next question is, how much post-processing is required to finish and resurface the cavity surfaces?
We don't do any post-processing on them.
To update the finish on the molds? No,
we use them as printed.
Yeah. There's no secondary sanding or
no
anything else yeah.
No, they're used as printed.
What resolution do you print at on the tools?
The medium resolution, the UHD, I believe it is.
Yes. So there's another question on factors that limit the life of the molds. So you said earlier that there's 5 to 200 pieces per mold, and so their question is what factors go into the number of parts.
Geometry of the part, if it has real thin little standing sections, things like that, eventually you're going to snap them. That's the geometry of the part is usually the limiting factor. And somewhat with the material. I mean, if it's easy to eject the material, in the case of the elastomers and that, we get a lot higher tool life. It's part specific. It's generally not, you know, most of the orders we're doing are development parts. Most people want 5 pieces, 12 pieces, maybe 20. They're meant for development projects. This isn't volume production kind of tooling. It's meant to be used for development, get real quick answers on testing. I'm doing a set of molds right now. We're doing 7 molds. They only want like 5 to 10 pieces off of each mold, but we're also going to ship them all 7 molds probably early to mid next week.
Great. So the next question we have is, it's a question on overmolding, and if it's been done successfully, and if you could comment just on the general process of overmolding.
Yeah, we've done it on several. We've done it with metal. We've done it with fiber optics. We've done it with plastic tubing. I actually did some Teflon tubing that was 2,000 thick. We overmolded that. Pretty much anything you could, within reason, anything that you could do in a metal mold, you should be able to do with these. Everything is part specific, but we have overmolded with it. Elastomers, polycarbs over the Teflon tubing. We've overmolded LCPs over contact. It just depends on the part, but it works very well.
So we have another question here. Actually, we have a few of them on handling shrinkage of the material of the mold and then shrinkage of the parts inside the mold that are injected.
Exactly the same as in any other mold.
Great.
You just figure in the shrink for the material. And
On the printing, do you see shrinkage of the tool when you print?
no, none of it's processed properly. Once there's a compensation for it.
So another question we have is, why did you choose the 3500 HT Max over other printers?
Quality of the print and the cleaning. A lot of times, like if we're doing insert molded contacts, we'll print up a mock-up of the contact block assembly with the metal parts in it. I could print these models. The contacts are only 6 thousandths thick. All right, and I'll print them in there, clean them, and have a contact block with the 6 thousandths thick contact in there that I could deflect. You know, it doesn't give you the contact force, but you get a little deflection. You could test it into assemblies. So to be able to clean a part that's only 6 thousandths thick and then use it, that's really why we pick these printers. The resolution and the quality of the prints. I don't think any other printer would really be able to do the surface quality that we're getting from the molds. We have looked at others.
So there's another question on, and I think we answered this before, but they're asking, is there any plastic material you cannot mold? And then they're asking particularly about Ultem.
We haven't molded Ultem yet. I wouldn't be afraid of it. Again, the temperature profile is not going to be that much different than LCPs. You're still going to be in the 600-something range. It's going to push a lot harder, so I'd be sensitive to the how fine the detail is in a situation like that. If the part geometry required fine detail, we would probably look at inserting some of that with steel. We regularly do hybrid tooling, where the majority of the mold is printed. And then we'll leave slots or other areas where we'll create a steel detail and insert it in clearance pockets that we print in place.
The 7 mold package that I was talking about before that we're running right now, 3 of those parts have steel inserts in them, cores, just because of the depth of the core, well over an inch.
And we'll use mold release, you know, to get the parts out. So we treat it like we would a traditional mold.
So there's another question, and I don't know even if we've looked into it yet, is after a mold's printed, what's the shelf life of the part or the mold once it's printed? Can it be used like a couple months later, or does it have to be used immediately after printing?
They could put it as long as they want to store it. It doesn't degrade or anything. I mean, we've had molds that were months and months. Some of my sample parts that I use, no, it's not a problem. I'm not. I mean,
We're not seeing it.
yeah, exactly.
Haven't reached it yet.
It's not like repeat orders 2 years later are a really common thing, but if you wanted to store the mold for 2 years, I'm sure it would still function afterwards. Again, we do development work, okay? Our life is measured in hours and days, not weeks and months, so.
So we have another question of how many versions of the mold do you make before you have a good working mold?
One. I will mold right off the table. I'm printing molds right now that will run production quality parts tomorrow morning. Okay, I ran one last night that's running production quality parts right now, and I'm going to ship those this afternoon. That was less than 24 hours from when I received the files. This isn't a random, it isn't a random process. When we make a mold, it makes the part.
Mm-hmm. So we've had a couple questions or comments on undercuts of the printed mold, and they're wondering if mold action is possible and then how successful you've been with it.
We've done them. The slides are always manually operated, and it's going to depend. Everything is part specific. I mean, if it's some huge, complicated undercut, I'm going to say no. A lot of times, similar parts, we'd say no in aluminum tooling too. It's part specific. We've done undercuts, okay? We've used slides in the molds. We've used core pins. You know, we've had multiple ones in the same mold, but again, it's part specific, but it is possible. Well, it's part specific. I mean, you know, something really nasty, it's probably, you know, it's probably not going to make, if it's very, very difficult to do in metal, it may be an issue in this too. There's some things we do that wouldn't be possible to do in metal with the elastomers. A lot of times we could actually mold up underneath things, you know, geometry that you couldn't cut into a metal mold without a lot of inserts. I could just print, the printer doesn't care, and then I could just roll the part out of it. So it's part specific.
Great. Thank you. So we had another couple of questions on if there's any warping during the printing, and
No.
does this create any problems? Yeah. Especially once it's under pressure, any slight warping that we've noticed, any slight warping would actually be compressed and dissipated with the pressure of the clamp.
No, if you're doing them properly, it shouldn't be good. We don't get the warping, so.
Okay.
And so I suppose you could get into a situation where you would, but it's nothing we've noticed.
So there's another question on mold release. I mean, is it required, and does it depend on the material you're injecting?
Yes and yes. Normally, it depends on the material. Normally, I'll use it for the same reasons you'd use it in a metal mold. You know, the world's just happier if the parts are coming out easier. We just use the standard mold release.
So we have another question on the multiple holes around the inserts and around the cavity. They're wondering what these are for.
Depending on the part and how I'm going to clamp, if it's a real short run mold, a lot of times I'll just screw the halves together. I could print the threaded holes finished, so I don't have to go back and tap them or anything. So it's so easy for me to print the dowel holes in, print some threads in, screw the two halves together. I keep everything at a standard height, so I just bring the nozzle down and shoot. Just makes life easier. Depends on the part. Most of the time we'll clamp with the ram, but sometimes it depends on the part. Sometimes I use screws. Again, we print all the holes. We could print it with the threads in them, so as soon as it comes off the table, I'm screwing it together. It's not like I have to do secondary machining on it. So there's really not a reason not to do that for a low volume. I mean, if you're going to run 100 of them, you don't want to be standing there zipping screws out. But on low volume things, I will use the screws.
Mm-hmm.
It makes setup easier.
So we have a couple of questions on part size limits, and then what you've noticed works well and what is out of the range for this application.
Generally, our molds are 4 inches square. Okay, if it's larger than that, we're going to have to look at it. I've done longer parts, but it's not going to do parts that are 12 inches square. It just doesn't. Generally, I'm running them in a 10-ton molding press. I've got X amount of clamping. So, I mean, you can't do huge parts. Mm-hmm. We normally do a 4x4 mold.
And the genesis of that was it fits about 80% of what we come across.
Exactly.
For the type of stuff that we're working on. So,
it depends. You know, most of our parts tend to be consumer electronic, medical, things like that, and that's the size range. We do some parts that are longer. That one tube we used an example, that was like 7.5, 8 inches long. So we do longer ones, but you know, you could only do X number of square inches with that amount of clamping.
So there's another question on if there's any type of cooling in printed molds.
No. I saw one come up about ejectors. We'll use ejector pins sometimes. That's fairly common, but we don't put cooling lines in the mold. The material doesn't absorb any heat, so you'd be waiting forever for the blocks to get hot, and then by the time you got the cooling lines close enough to your mold cavity, I think there's a good chance you could break them. This stuff does not transfer heat very well at all, which means it wouldn't remove it well either. So the cooling lines wouldn't really do much.
Yeah, and just a note on that, it's mostly because metal's a thermal conductor, where plastic is just in general, it's a thermal insulator. It doesn't conduct heat like a metal would.
Right, so, I mean, again, most of our molds are running 5 to 12 pieces, so they're not going to get hot. These aren't meant to be production tools. They're experimental tooling, and when it gets into higher volumes where you're going to need cooling lines and everything else, we go into a different kind of mold. These are for testing. They're meant to get you parts in one day. Mm-hmm. Or a couple of days, you know, but not to get you thousands and thousands of parts.
Great. So we have another question on if you've ever tried multi-cavity tools, and then what level of success you had.
Yeah, I ran, well, the 3 tools, the one I did last night, the 2 I'm doing today are 2-cavity. We did one last week that was a 4-cavity. Depends on the size of the part, how many of them I need to run. Even if I'm running real low quantities, if it's a real small part, the printer doesn't care. So I'll just duplicate that cavity a couple of times. I mean, you know, it's another 5 minutes of mold design. So, yeah, we do a lot of multi-cavity. It depends on this, you know, if it fits inside my mold block, I'll add in cavities.
So there's another question on if there's any special way of positioning any metal inserts into the mold blocks, and if you have to do anything different than you would with a metal tool.
No, we actually print the gauging for the metal inserts right into the tool. So it pretty much locates them exactly like you would in a metal tool. We'll put a carrier strip on them and locators, and what you would do in a metal tool, you do in the plastic. Locate them almost exactly the same. We don't do anything really special. It's the same process we would use in the metal tooling, because generally that's what we're trying to duplicate. It's how these parts are going to run in production. So we try to use the same process.
So we have another question on shutoffs versus a metal tool. Like, do you have to do, there's been a couple of questions on any differences between metal and plastic as far as mold design goes.
Metal's heavier. Not really. We watch our wall thicknesses, but no, we just clamp them up. I mean, it's not, you're building it with a different material, but the same rules apply. We don't do anything special on them. I do watch the wall thickness because of the material that I'm building the tools out of. But as far as clamping, depending on my volume, you know, if I'm running more parts, I come down and clamp it with the ram just like I would. If we get up to 10 tons of clamping, these molds really take the pressure. So it's not a process. It's not a problem for us to clamp the mold itself in the press. On the real short run stuff, I'll use screws, but there's nothing special required. We use standard vents, gates, pretty much exactly what you would do in a metal mold. Because we run metal molds through the same presses, and they're basically the same designs.
Great. So we have another question on how do you decide to print and do the injection molding process versus directly printing the part?
If you're going to use printed material in your production part, that makes sense. If you're using an ABS or if you're ABS, LCP, something like that, where you can't get those material properties off the table, or a Santoprene, we're running production material through these molds, so you get exactly the same part you'll be using in production. The printed parts give you something to look at and hold and everything, but it will not perform like a production part. So that's why we do this. About the only, we hardly ever run parts off that table. It's very seldom. If we want examples to bring to a meeting, things like that. I know a lot of people run samples. Our machines are usually so tied up running molds that we don't get into it. But that's what drives the molded parts. We could use the production material, so we don't have to wonder how it's going to perform. It will perform exactly the same as what you're going to make in a production mold.
All right, and JP, we should probably wrap because we're at the top of the hour.
Great. Okay. Well, I think that's all the questions that I wanted to go through.
Great. Thank you, John Paul. Ray and Frank, thank you so much for spending the time here with us today to share how you've been successful using the Project 3500 to make printed molds. We really appreciate your time. We love having you as a customer. Thank you so much. And everyone out in the audience, thank you for spending an hour here with us today. We hope this was educational and informative. And a recording of this session will be available. We'll send you an email either later today or tomorrow with a full recording of this. So you're welcome to watch it again, to share it with friends and colleagues, whomever you might think would be interested in this information. Feel free to share it around. Of course, we'd love to have you doing that. And we will be following up with you after. You'll be getting an email, and if you expressed interest, you'll be getting a call either from us or from BuyLink or from both of us to discuss more detail. Again, thank you, everyone, and have a great day.
Thank you.